Okay, so I'm just going to wait another 30 seconds or so before starting. I'm a bit disconcerted I can't see my own video stream, but I hope it's on and that you can all see me and hear me. So it's exactly the same logistics as last week. We are recording the session. We're running it in webinar format, so I don't have to instruct you to turn your cameras off or anything like that, because I don't believe it's possible for you to turn them on. Questions are welcome in the chat or the Q&A tool as we go. There may be some time for Q&A at the end, but I will certainly be checking questions as we go, and I won't sign off until everything's addressed. Or whether that happens before or after the end of the session depends on how much pace I get through these things. It's the same link to the slides as last week. We've put in a new PDF into that folder so you can follow along with the slides. So yeah, that's it. We will kick off. So this is a slide you saw last week. It was the introduction that told us that real-time is about as being as fast as specified, and we looked closely at the differences between general purpose and real-time loads, and the fact that we want to have these quite separated in the Linux world. And I told you last week that Linux can be configured in multiple different ways to allow you to choose the right trade-off between system performance and worst-case latency. And that is what we're back to talk about this week. So just as a very quick reminder, I've put our kind of example real-time system on the screen again. We will not refer to this nearly as much as we did last week, because last week we were looking at essentially the barrier, the kernel user kernel interface between these two worlds, which we're not looking at. We're looking at almost exclusively in the kernel this week. So we will mention this from time to time, but not nearly as frequently as we did last week. And a quick summary and reminder of one critical thing before we start looking at things like preempt RT and other mechanisms to try and reduce latency in the kernel. We want to be clear that Linux user space will always be running with interrupts unmasked. If you are in the user space, that means you are executing in user space, you're not in a system call, then you will always be running with interrupts unmasked and capable of being preempted at any time. So regardless of the preemption model you have for code running in the kernel, user space is always preemptible. Everything we talked about last week, the different schedulers, real-time priorities, everything always impacts user space code. And then finally, this is again the little wheel that we saw last week while we were setting the scene. Last week we kind of looked at things like POSIX, systems integration, and we talked about memory management. This week, primarily, we're going to be talking about the scheduler. So a scheduler is a fairly simple piece of code when it's all said and done. The heuristics and the impact on the system is enormous, but the actual nature of the code. Its job essentially is to treat the CPUs as a resource, and based on whatever policy we have in place, allocate those resources to tasks that compete to use the set of CPUs we have available to us. And the kind of lenses that we might like to use to think about the scheduler are these strategies, the occasions, and these metrics and algorithms. So the strategy is the fundamental policy of how we're going to allocate CPU resources. So we have a strategy with CFS, which is all about fairness in allocating how we present the CPUs to the tasks competing. Obviously, we have the real-time strategy, where our goal is to have the highest priority tasks running on the available cores, and then deadline and something. So those are our strategies, which are essentially the tools we looked at last week, the scheduling classes. Scheduling occasions, I quite often call this as scheduler being asked to make a decision. This is the point at which the scheduler is going to actually look at the set of runnable tasks and figure out what task should be running on a CPU at any point. So it's being called upon to make a decision about what to execute next. And then finally, we have algorithms and metrics. So algorithms are the kind of low-level details of how we realize our strategy. And metrics, things like runtime, load, are tools that we can use to decide what is going to run next. Within the Linux kernel, as I've mentioned, there are scheduling classes, and we looked last week at the 3 ones that you use as a user. And I mentioned there are 2 additional scheduling classes that wrap around this. So we have stop, which is the highest priority scheduling class. It's used to do things like migrate tasks to other CPUs and to do things like CPU hot unplug. So when you want to turn off a task or you want to remove junk from the run queues, that's usually the most important thing you need to do. So we get those available and shifted over to other cores. And then we start working through our real-time workloads. At the bottom opposite end, we have idle, which is basically what we're going to execute if there is no useful work for us to do. And the role of idle class is to identify and estimate how long it's going to be in idle for and make the appropriate power saving decisions to try and minimize power while we are not doing any useful work. So again, we've got our stop and our idle now wrapped around the top, and you'll notice, as is fairly obvious from last week, that there is no scheduling policy attached to these scheduling classes. So they're classes inside the Linux kernel, but there is no scheduling policy attached. There's no mechanism to talk about these schedulers from user space because they're not relevant to user space. The other thing, again, I'll remind as we step into these sections that as we're looking inside the kernel, we'll start to talk about the normal scheduler, CFS, as shed normal, whereas shed other is the name that you tend to see in the POSIX standards. And since we're starting to look inside the kernel a little bit, this is the absolute heart of the scheduler, which we brought up mostly to show that it's not, terrifyingly difficult code. If you've got a source navigator, if you understand the sort of finger operator and calling by function pointer, we basically have a for loop that walks through the 5 different scheduling classes and tries to pick a task. And if it picks a task, it goes and executes it. And if not, we continue around the loop. Since the idle task should always pick out a task, this should actually usually always exit via the path here through return P. And it's what executes when we are called upon to make a scheduling decision. This is the thing that executes when we reach one of those scheduling occasions. And like I say, it's very readable. I don't want to encourage you to view the scheduler as magic. If you want to, tuning the scheduler can be very difficult because you've got lots of competing demands to meet. But understanding how the current one works is very, very readable. So I would encourage people, if they're interested, to take a look at this kind of thing. In terms of measurements that can inform scheduling decisions, this is a very, very simplified view of a 4-core SMP system. So we start off with tasks that are sleeping. They're not competing for CPU resources, and we need to make this task here runnable. So the first thing that's going to happen when it becomes runnable is there has to be a decision made about which CPU to enqueue it on in order to share the load most reasonably across the system. So when it wakes up, we have to look for essentially the lightest loaded CPU and try and load it onto that CPU, unless there is some other reason to make decisions like minimizing power. But in general, we're looking for the most idle CPU, and that's where we're going to wake it up. That's based on this thing on the right-hand side, the PELT. It stands for per entity load tracking, and it's estimation of how costly each of the tasks in a run queue is. And by summing the tasks in a run queue, we can estimate how busy the CPU is. And by looking at the load of the newly woken task, we can find out where it's best going to fit in the system. So PELT is an estimation of the cost of each task. The run queues here, incidentally, are grossly simplified because we're showing them as simple linked lists. As we work through the scheduling classes, the data structures that we're showing here as linked lists are in fact much more complicated than that, but we'll get to that in a minute. So PELT is one of the major measurements that inform scheduling decisions, and the other major tool for scheduler decisions is this V runtime, which is simply the estimated runtime that a particular task has spent on a CPU. And the fundamental goal of fairness is to provide each task with the same amount of runtime. So V runtime is the metric that measures how much time tasks have spent executing. So The difference between kind of V runtime and per entity load tracking is that V runtime is simply an accumulation of runtime, measuring the entire time a task has been running. Load tracking is a decaying value that gives us some sense of how costly that task is going to be to execute. And it means that things like tasks that densely jump together and then sleep for long periods are viewed as having a different weight as a task that pops up with a really fixed regular heartbeat. This will be considered, depending on where you study the load, as a higher load because it's denser packed. So with that, we can get and look at the default scheduler, the completely fair scheduler. Just as we did last week, we're going to try and show what helps the completely fair scheduler do a good job for baseline tasks before we look at the tasks we're going to switch and push into the real-time scheduler. So we've got our 3 scheduling policies, but they all have very much the same effect. The whole system hinges on the accumulation of virtual runtime, which is how long the task has been run for. And essentially, the task with the shortest virtual runtime will be the highest priority task. So we sort the runnable tasks by their virtual runtime, and the one whose runtime is lowest will win out, and that will be given the CPU. If you were curious about nice values are ultimately, for the completely fair scheduler, a multiplier that is attached to the accumulation of virtual runtime. That's why it's called virtual runtime, because it's not actually the wall clock. It is the wall clock time consumption multiplied by the task's weight, and the task's weight comes from its V runtime. So that if you have a high weight, the V runtime increases slower, and we get a bigger share of the CPU. So the result of that is that with a better nice value, you get a distinct share of the CPU. But other than that, the fairness comes after we've multiplied the weights. The fairness comes in balancing the virtual runtime. Newly added tasks. So if you think about this, what you do not want is if you've got a batch ray tracer running the background that spent 3 hours drawing your picture, and you add a new task to the system, you don't want a situation where the ray tracer now has to wait 3 hours for more CPU. That doesn't really seem fair, because nothing else was competing with it in those first 3 hours. So for newly added tasks and tasks that are made runnable after sleeping for very long periods, there's this concept called the minimum V runtime. So the minimum V runtime is a monotonically increasing value that tracks the smallest V runtime among the tasks within a run queue. And when a new task is made runnable, its virtual runtime is compared against the min V runtime and boosted up to that level if it sits behind. So when we start competing, we will start tracking the runtimes. But when we're not competing for the CPU, we do get this jump in our virtual runtime to keep things balanced, so that it's only when there's competition for the CPU that we actually have to maintain fairness. Other than that, the run queue is actually a run tree. So the run queue in a CFS system is a red-black tree. A red-black tree is a type of self-balancing binary search tree. And as a self-balancing tree, that means essentially all of the actions that you can perform in it have a complexity of log n. So searching, because it goes out breadth-wise, we get a log. If we want to find this leftmost task, that's always going to be log n for the number of tasks in the run queue, the complexity of that. And similarly, actually, insertion and removal is also the same complexity. So that's reasonable. Log n is not too bad. As the number of tasks grows large, we don't grow proportionally, we grow with the log. Red-black trees are themselves very interesting data structures. I'm not going to go into them in detail here, but if you want to study how they work from a kind of computer science perspective, the Wikipedia article's very good. It's worth a read, and there's some terrific animations on YouTube showing how the tree pivots when you do different types of insertion. So red-black tree is basically a binary tree into which 6 rules are applied, and those rules cause it to self-balance in a way that maintains efficiency long-term without having awkward worst-case boundaries. Unbalanced binary trees have to be rebalanced, and the rebalances become expensive, whereas a self-balancing one maintains the balance over time without exploding in complexity. If you really want to dig deep on the nice levels, there is simply a map that matches the nice level to the weight, which is the rate at which we accumulate virtual runtime. Within the specs, so within the POSIX standards, the meaning of nice is left very vague, which is why I didn't describe it last week. When we were covering the user kernel interfaces, I didn't go into detail of how much a task is favored by being at a nice level of 19 and how much it's disfavored at a level of 19, how favorable minus 20 is. But you can see that with these weightings. These are the rate at which we accumulate v runtime, and you can see that the nice level of 0, which is the default, 1024, is essentially saying that natural v runtime accumulates at the 10th bit or 11th bit. It's basically designed so that each step between causes a 10% changeover of CPU. So if you've got equally nice things, you'll get a 50-50 split. If you have one nice level of distance difference, you'll have a 40-60 split. And then the relative difference goes up and up and up over time, and it's arranged so that every step goes this 10%. But that means if you move 2 steps, you're now moving past closer to 25% of the part and so on. And you can see by the time you hit the extreme weights, so a nice of 19 is going to get very little of the CPU compared to level 0. That allows me to do something like kick off some big pars in the background at a nice level that's very low, knowing that my interactive builds won't be too badly hurt, because as soon as my interactive builds running at 0 compete with my priority 19 tasks, my nice 19 tasks, I'm going to get the dominant share of the CPU, and my interactive activity is going to be comfortable. Likewise, if you are renicing something to minus 20, it's going to get a absolutely dominant share of the CPU when it's competing against things at nice level 0. So that's just the factors you can use. It's how you can be confident that when you set something to say shed idle, which is even lower weighting than this, it really does mean that it's not going to get very much CPU when it's competing. So moving on from that, the real-time scheduler. So the real-time scheduler is by far and away the simplest scheduler within the system. It has a runtime task priority range. I will note that it's inverted. So in user space, 99 is the highest priority task in the system. That gets flipped over inside the kernel, and 1 is the highest priority. I have to admit, I haven't studied the historical reasons why that is. But that is the way it goes. I could make a guess as to do with finding least significant set bits is more efficient on a wider range of platforms. It could be something as simple as that. So we've got our 2 scheduling policies, shed FIFO, shed RR. We talked about the time slice last week. So the default time slice for a round robin task is 100 milliseconds, but it's tunable. If you tune it down to 1 millisecond, however, you won't achieve a 1 millisecond time slice unless you modify the default value of config hertz. Config hertz will default to 100, and that means the scheduler tick, which we'll talk about towards the end of today, happens every 10 milliseconds, and round robin tasks, regardless of the setting of the syscontrol, can only be moved when the scheduler tick goes off. So you can set this from somewhere between several thousand down to 1 millisecond as an interface, but it will clamp to 10 milliseconds if you have config hertz set to 100. The real-time scheduler itself is purely a set of linked lists and a bitmap to say which of those lists has something in it. So it's 100 odd linked lists and a bitmap saying which one is non-empty. That gives you a runtime complexity essentially of 01, because the search of the bitmap is complexity 1, and then the extraction of the head of the linked list also complexity 1. It looks like this. If you just want a visualization, we have a bitmap, and that's got our hot queues. So here we have the priority 1 queue. It consists of 3 tasks, a FIFO task, a round robin task, and a FIFO task. That itself is likely to be a sign of a misdesigned system, because if you remember the FIFO tasks, they never give up the CPU unless they voluntarily yield, whereas a round robin task will forcibly give up the CPU once it hits the end of its runtime. So in other words, the 2 FIFO tasks here are more likely to take the CPU because they will never give way to the round robin task. I also mentioned last week why I think round robin is of limited use for well-designed real-time systems on Linux. Mostly the base load should be running on the normal scheduler anyway, so time slicing isn't needed for anything related to fairness. And if you're relying on the time slice of round robin to make your system real-time correct, there's a chance it's been misdesigned. Not guaranteed, but there's a chance. So my default is always to pick shed FIFO unless I'm steered in a different direction. And then finally, the deadline scheduler. So the deadline scheduler has a couple of things in common actually with the CFS scheduler, and that is ultimately that its run queue is a self-balancing red-black tree, and it's got the same O log n complexity as a result. The difference ultimately is the sort key. So the sort key for the CFS scheduler is based on the virtual runtime. We're looking for the minimum virtual runtime. And the sort key for the deadline scheduler is the deadline. So the earliest deadline moves to the left of the tree, and that's the one which we will schedule first. The deadline scheduler does have a little bit of additional activity related to verifying whether you've stayed within your deadline. So when the scheduler ticks, we check to make sure our deadline has been not overused. But other than that, the scheduler is simply a red-black tree, and run queue is sorted by the deadline. Now, we wanted to dig a little bit deeper just to follow up on my assertion I made last week without proving it, if you like, that the deadline scheduler makes it possible to schedule workloads that cannot be scheduled using the real-time scheduler. And there's an example. This is a single CPU system. It's running 3 tasks, and our tasks have a worst case execution time, 1, 2, and 3 milliseconds respectively. And we've got a period of 4, 6, and 8. And in this case, the deadline is also the same as the period for convenience. So if we look at the visualization on the bottom left, this is what would happen if you try to map that onto the real-time scheduler. So we've done that by making T1 the highest priority task in the system because it has the shortest deadlines. And then we've moved to T2, slightly more relaxed deadline, T3, further relaxed deadline. That's the priority order that seems reasonable to set the system up at. And what happens is T1 gets extremely good service. T1 is always going to trigger when the thing goes off. It takes the CPU, it does its milliseconds work, it sleeps for 3 milliseconds, then it goes off again. So you always get an absolutely jitter-free, regular scheduling pattern for T1. T2 has to give way to T1. So when T1 and T2 fire simultaneously, it has to wait until T1's finished, and then it gets the next byte of the CPU. So it always runs in chunks together as it happens, but it sometimes has a gap before it runs, deferring to T2. But only when they fire simultaneously. When they don't fire simultaneously, it gets the CPU straight away. Again, it gets reasonably good service and reasonably low jitter. The problem is T3. So T3 only gets to execute 2 milliseconds before its deadline, because between them, T1 and T2 have consumed 6 milliseconds of processing. And as a result, T3 will not be able to meet its deadline. By the time its deadline is reached, it's not done enough processing to complete its deadline. So that system isn't schedulable. You can't correctly schedule that system on that particular scheduler with only 1 core. So what happens to the deadline scheduler? The deadline scheduler is different. So all 3 of these tasks are triggered at the same time in the first instance, but they have different deadlines. So they sort based on the deadline, and that produces T1, T2, T3 priority. So T1 and T2 behave exactly as they did for the real-time scheduler. But once we hit T3, it doesn't just get 2 milliseconds, it gets the full 3 milliseconds because its deadline was queued first, and it happens to be the same as T1. And if you look at these, even if T1 did take the CPU, it would still have completed its 3 milliseconds of processing before the deadline, because it's also shorter than this one. And that continues up through. You can look at the patterns, you can study them. You're always looking forward to try and figure out what the deadline is, and then you can see which one is the most important in the system at any particular time. So for example, at this time instance here, then this task is the lowest priority task in the system because its deadline's a long way ahead, which is why it's deferring to the other tasks. The other difference, of course, is that T1 is experiencing quite substantial jitter. So the delay before it does its processing varies between 0, 1, and 2 milliseconds. And that's okay, because that's within specification. Right? We're about as being as fast as specified. So although we do observe significant jitter in T1's timing, there was no requirement that we had to avoid jitter in T1. If we wanted to avoid jitter in T1, we'd have to reduce the deadline. So the deadline is what you can use to avoid jitter. That's why we have the period and the deadline separately. And you could configure this so that the runtime is 1, the deadline is 1, and the period is 4. And then T1 would get a perfectly correct scheduling. Whether the whole system would become schedulable, you might not be allowed to admit T3 to the scheduler, because it might fail the entrance checks. But it can be interesting to play these things. And these little graphs, if you get a bit of graph paper, it can be interesting to look at the effects of these things, so you really understand how it's going and doing its thing. I'm not going to talk very much about the special schedulers. So we have the stop scheduler. The stop scheduler appears in the task lists as tasks called migration divided by the CPU number. Like I say, it's largely used for task migration and CPU hot plug. But you might, like I say, you only really see it because it appears as a task within the scheduler. And likewise, the idle class, the lowest priority task in the system, will appear as threads named swapper divided by the CPU number. And they're going to hook into things like CPU idle and the hot plug system to figure out what's the best way to minimize power when we are idle. So that was the quick summary of how the different schedulers are implemented. I'm just going to do a brief tour of contributors to latency before we start talking about preemption evolution, so we can see which of those latencies the preemption evolution helps us to address. So there's lots of different ways to talk about latency. We've split it out into 5 different latency sources, some of which preempt RT helps us address and some of which it doesn't. And we're defining latency in this case as the amount of time in which a task is theoretically runnable but not executed before it reaches its completion. And theoretically runnable doesn't mean the point at which it becomes runnable in the scheduler. Theoretically runnable means the point when the event that is going to make it runnable has been triggered. So the external interrupt or the timer going off has happened. At that point, whether or not the scheduler knows the task is runnable, the chain of events that is going to make it runnable has started. So we're going to call that theoretically runnable. And that roughly means that the interrupt has happened. If we are in a low power state, there might be some delay before we can switch into normal running state. By the time we're in normal running state, there is some intrinsic hardware interrupt latency of how long it takes us to react to an interrupt. And there's also potential for latency caused by interrupts being locked. So if interrupts are locked, we might have to make a long period before we can start our interrupt handler. Once we're in the interrupt handler, we're going to make the task runnable. So we're not measuring time to service interrupt, we're working to time to service thread in this particular case. So the deadline for the system is not just handling an interrupt, it's handling an interrupt and then reacting to it from a task of some sort. So after we make the task runnable, this is where it becomes runnable to the scheduler. So the first 2 are kind of theoretic latencies. After this point, everything's runnable and the latencies are visible to the scheduler. So we have a scheduling latency. That's both the cost of scheduling and switching a task together with the period of time during which preemption is forbidden. So the nature of preemption evolution is it's reducing the periods where preemption is forbidden. and that is how it contributes to significant improvements in latency by eliminating scheduling latency where we can't preempt. And then finally, once we've reached the point where we can preempt, there may be application latency, which is other tasks competing for the CPU. So although we're runnable, we're ready to make scheduling decisions, T1 still can't run because there's a high priority task pending. That's application latency. There's nothing the kernel can do about that. But from the point of view of the design of the T1 task, which contributes to the real-time system, we do have to consider whether we have high priority activity to complete first. And then finally, if T1 were to wait for a semaphore or mutex, I think we'll call that a mutex, it's much clearer. If T1 is waiting for a mutex, there will be potentially priority inversion latency as well. The reason I don't like semaphore in there instantly is semaphores can't implement the priority inheritance protocol, which means if you were to use semaphores in your design, priority inversion is unavoidable. And therefore, that's why I wouldn't encourage the use of semaphores in any but sort of theoretic systems or where they have to be used. Okay, so scratching and digging just a little bit deeper, wake-up latency isn't purely hardware. It's not purely the time it takes for the hardware to get kicked and for the CPU to come back to life, because during that path, it might well be executing firmware. It might have hit into the PSCI systems, which are implemented in trusted firmware in EL3. So it doesn't necessarily mean pure hardware latency. It means the cost of receiving some event and getting the CPU running again. Interrupt latency, like I say, hardware latency does exist. There is a few cycles needed for CPU to capture the original program counter and stack pointer and swap in whatever else is coming. But the predominant contributor to interrupt latency comes from two sources, one of which is other interrupt handlers, especially on Linux. On Linux, all interrupts, until we introduce preempt RT, all interrupts run at the same priority and are dispatched in an undefined and potentially unfair order. Undefined is a principle. All the drivers are written on the assumption that the order that the interrupts will be dispatched if they're competing is undefined. In reality, it's closer to architecture defined. So on an ARM system, when you've got multiple interrupts firing into a GIC and all those interrupts are the same priority, the GIC will pick the one which is the smallest number SGI. Not SGI, sorry, I beg your pardon, SPI, shared peripheral interrupt. So the one that has the lowest number is the one the GIC will select. The other aspect is that, again, on ARM systems, CPU 0 typically handles all of the interrupts. That's a trick to save power because it allows other CPUs to go into deeper sleep states because we know that interrupts aren't going to wake them up. There are ways, therefore, you can tune interrupt latency a little bit by assigning critical CPUs to particular CPUs. So that's usually done as a performance booster on non-real-time systems. You simply say, right, that interrupt's really important. I'm going to give it a separate CPU to handle it. It will then share it with other scheduler tasks, but the interrupt will then see much less latency because it's not competing with other interrupts. The other contributor to interrupt handlers is interrupts being disabled. So spin locks come with the standard spin lock variable and the spin lock and disable interrupts if you want to share that spin lock with an interrupt handler. So it is those critical sections prevent interrupts from arriving, and they are a contributor to interrupt latency. The final thing that we should mention while we're talking about interrupt latency is during interrupt handling, there is no opportunity to boost the CPU frequency. So CPU frequency in modern systems is driven by the scheduler. So interrupts happen outside the supervision of the scheduler, and therefore, even if the interrupt load is high, the scheduler can't react necessarily and cause the CPU frequency to go up. So there's not really a great deal can be done about that except making sure that the minimum CPU frequency you tolerate is sufficient to meet your real-time specification. Scheduling latency is going to be the topic of a good deal of what I'm about to say next. like I say, the cost of actually finding a task isn't too bad. The delays that happen if preemption has been suppressed, and therefore we're not running the most important task that we need to run, do contribute quite significantly. Application latency is not my problem in this particular kind of blinkered view of the world. Application latency is the application author's problem, which is occasionally me, but in this particular presentation, I'm saying it is somebody else's problem. They have to design the system, they have to get the priorities correct, they have to make sure they've designed it so the low priority tasks don't get denied CPU by high priority tasks. That prevents them from meeting their deadlines. And then finally, priority inversion latency we talked about last week, and we expect it to be fixed by using priority inheritance. So that's the kind of scene setting study of latency analysis. We're now going to look at the 4 different models that Linux supports for different types of preemption. Before we get started, Linux does support 4 models, but there is work ongoing to introduce a thing called preempt dynamic. So there's still the 4 models, the 4 that we're going to talk about. Preempt dynamic prevents you having to pick one ahead of time. So currently, when you compile the kernel, you compile and burn in the particular preemption model you're going to use. You can't change it at runtime. That is not a good suit for distributors. So distributors like to ship just one kernel. And so preempt dynamic, I think, is a mechanism to allow you to change at runtime between the first 3 of the preemption models we're going to discuss. So that's all we're going to say about preempt dynamic. It doesn't actually change any of the concepts and principles I'm about to tell you. It just moves the decision point from being during compile, and therefore it's a kconfig option, to being at runtime, and therefore it's a kernel command line option. So thus far, I've talked about preemption as though it's just a thing that everybody understands. But I would like to give a slightly more formal description so that we can contrast it against voluntarily descheduling. So preemption is the act of temporarily suspending the executing task in order to perform some alternative work. And the way we're going to talk about it at the moment, that decision to suspend is not made by the task itself. Somebody else has said, right, I need to stop that task, and we're doing it without the cooperation of the task. So in other words, when a higher priority real-time task is made runnable, the scheduler will immediately stop the current task from, well, if it's on the same CPU, will immediately stop the task we're currently running and run the new higher priority task. Technically speaking, interrupt handlers also preempt tasks. They are an involuntary suspension so that we can go and handle an interrupt. That's a sufficiently common behavior, interrupting, that we're going to use the more specific term interrupting. So when we talk about preemption, we are talking about a task preempting another task, not an interrupt preempting a task. So it would not be wrong to talk about interrupt handlers as preempting the task, but I'm going to try very hard not to say that because it just makes things a little confusing as we work through the material ahead. The alternative to that is voluntary descheduling. This is a task choosing to step back and allow somebody else to take over the CPU. And that comes in a couple of forms. Obviously, sleeping is the fundamental form of voluntary scheduling. If you go to sleep, you're no longer on the run queues, you've given up the CPU. You can also call special APIs, such as yielding, that cause you to give way to potentially other tasks. If you're interested in computing history, you're probably aware that multitasking as a concept can be implemented using either or both of the above approaches. So prior to things like Windows 95 and Mac OS System 9, sorry, you didn't have preemptive multitasking on desktop operating systems. So these are right back in the late 90s. And they all worked on cooperative multitasking, which sounds nice, but because everything relies on application cooperation, as soon as you get a bug, things fall over very quickly. So the dominant model for anything but kind of fixed purpose microcontrollers has moved over to this kind of involuntary preemption model. And that's quite important to understand because one of the concepts we're going to look at is voluntary preemption as a concept. So many of the drawbacks that voluntary preemption and voluntary multitasking has, I'm just bringing it up so you can try and map. If you're aware of these differences, you can kind of map them to some of the things we're about to talk about. So the 4 models. The phrasing we've used in the left in bold is taken directly from kconfig. So these are the phrasings that are used to describe the config options that you have available to you in the kernel. So the first one is not to have any kind of forced preemption of kernel code. The effective result of that is that preemption only exists when you are executing a user space. As soon as you make a system call, it is now your CPU until that system call either causes your thread to sleep or you complete the system call. So if you call some expensive action like say fork, which clones the virtual memory address space of a process, when you call that relatively expensive option, relatively expensive system call, it's your CPU until the fork has completed. The next level up is voluntary kernel preemption. And this is analogous to voluntary multitasking. So in other words, there will be particular points within the kernel at which we offer to give up the CPU to other things. So during a system call, if it's a long-running system call, we hope to execute these points quite frequently, and we can use them to voluntarily give the CPU to somebody else. The third form is what we call the preemptible kernel. Oh, incidentally, these things in quotes are suggested use cases. So the idea is that a server doesn't really need a low latency mouse or anything like that. So you don't need forced preemption. Voluntary kernel preemption is called quite often desktop. And that is the reality. I mean, I am talking to you now through a desktop Linux operating system that is running with voluntary kernel preemption. It's the default setting for a lot of distros, unless they've got a really strong server focus. The preemptible kernel is again analogous to the other form of multitasking, so preemptive multitasking. At that point, the default behavior is that if a task is made runnable, it will preempt unless there is something suppressing it. And then finally, we have the fully preemptible kernel, which takes that same concept that we expect to be able to preempt at any time, unless there's something suppressing it, and try to get rid of as many of those things that can suppress preemption. So in the third case, we are preempting whenever we can, unless it's suppressed, but we haven't taken any steps or very many steps to minimize the windows in which we suppress preemption. And roughly speaking, that gives you a decreasing worst case latency. So as you go down towards fully preemptible kernel, your worst cases will get much better. Worst case costs, lower is better, so decreasing is good. Unfortunately, as you work down the right-hand side, you will probably also see decreasing overall system performance, which is why it's not just, let's pick preempt RT. It is much more complex than that. We have to make the decision about the correct model. Just a quick aside into history. So how did these motivations models come about? I mean, it's fair to say that the early Linux, meaning kind of turn of the century Linux, was not designed for real-time processing. It wasn't what it was for. And it was at that time designed for fairness, throughput, and kind of resource sharing of machines like servers. And so this was a quote from a survey done about the possibility of Linux being used in the embedded server market before it was really fashionable to do so. This is kind of 2004. It was being thought about. You know, I was involved in designing Linux systems at this point, but it wasn't obvious and taking over in more and more and more markets. It was early stages. And you look down this list, and it is very noticeable that concerns about the real-time limitations were the dominant concern about the factors that would inhibit the adoption within embedded markets. Even beyond GPL concern, which again, a lot of companies were not comfortable with the GPL license at this stage in history. And so even higher than that were concerns that it simply didn't have the technical underpinnings that were necessary to be useful in the embedded market. And that kind of maps into this kind of history here. So this is the very earliest 1.x series kernel, where there was no preemption whatsoever. There was no preemption, there was no SMP, nothing of those nature. We then move it into the kind of 2.x era, 2.0 era. There was still no preemption model, so everything was just you make a system call, you own the CPU. But a thing called the big kernel lock was added to provide initial SMP support. The big kernel lock was basically a single spin lock that was used to prevent two SMP cores running kernel code simultaneously. It's as simple as that. So you could run user space simultaneously on your SMP cores, but as soon as you jumped into the kernel, you'd hit the big kernel lock, and that would mean that effectively only one core could run in the kernel at once. If you're curious, this is actually very analogous to things like the Python global interpreter lock. So during the next couple of kernel releases, there was still no preemption of kernel code, but that big kernel lock was being recognized as a significant performance hazard for SMP machines. Because if you're doing various activities, file system heavy stuff, you need those two cores to be in the kernel simultaneously. So fine-grained spin locking started to be introduced across the kernel. In this era also, there was work being done on the preempt kernel 2.4, which was an experimental kind of kernel that allowed kernel preemption to take place. So it was based on spin locks. Once you have the spin locks introduced for SMP, the fine-grained locking, you can use those same spin locks to suppress preemption. The nature of a spin lock is that preemption is unacceptable while you own a spin lock, because if you allow another task to run and there's competition for the spin lock on the same CPU, the spin lock can't be acquired and you're stuck. Spin locks work on the basis that they're only contended for by multiple SMP CPUs, and therefore they can be released fairly quickly. So it's, from the SMP point of view, it's safer to spin than to try and sleep, because sleeping is potentially expensive. Whereas if you know that the lock is only going to be held for a very short window, we could just wait for it. So that was the sort of thing that was happening at that stage, 2.4. And in 2.6, this introduced the preemption models that were being trialed through preempt kernel 2.4. They were all merged in. They became available to many developers at that point. That's where we get, config preempt voluntary and things like that were being introduced. This is a series, incidentally. So the kernel 2.6 was the first time we went to the the first time the kernel adopted a rolling model. So before that, it followed a stable, unstable approach. So all the kernel development for 2.6 was originally done as a kernel called 2.5. But when kernel 2.6 came out, it was a rolling development, just as we have today. So when I'm describing some of these features, they did not all arrive at the beginning of the kernel 2.6 era. They were introduced during its rolling development. So kernel preemption was introduced. The big kernel lock was made preemptible. What that basically means is the big kernel lock switched from being a slightly weird spin lock to being a slightly weird sleeping mutex. And by slightly weird, I mean that it was under the covers, I think, a hybrid spin lock and mutex that acted like a mutex on the same core and was automatically released when you tried to sleep. So it did have some very peculiar properties that a normal mutex and a normal spin lock don't have. And at that stage also, that's where the O1 scheduler that I talked about complexity a lot when I was talking about CFS and things like that. The O1 scheduler predated CFS. It was based on kind of heuristics to try and spot interactive processes and give them an actual physical priority boost. It would spot processes and say, all right, you've been asleep a long time. I'm going to dynamically increase your priority. You've been consuming lots of CPU. I'm going to punish you and demote your priority. That's how the interactivity was managed in the early or older kernels. At the same time in this era, kind of in parallel with the 2.6 work, the preempt RT patch set started to emerge for the first time. And the preempt RT kernel patch set has been around for a very long time. I think it's more than 12 years. And it's pioneered a lot of really useful kernel features. So this kind of preempt kernel thing started to try and make critical sections within the kernel, i.e. things that were spin locked. It was trying to make those preemptible as well. It was trying to avoid the IRQ subsystem from creating long periods of interrupt lock for certain processes. It introduced mutex locks based on priority inheritance to avoid priority inversion, high resolution timers, things like that. And then moving on from that into heading towards the modern era. So over that kind of decade, there was lots of things happening in the kernel, vast number, but some of the highlights were things. The BKL was finally removed. Technically, the BKL was removed in 2639, which was the final 2.6 kernel. But I view that as being close to the 3.x era, and it avoids confusion about the difference between preemptible and removable. So it was removed. It was gone in 3.0. Many of the preempt RT features that were developed within this patch set were landed in the kernel because they were generally useful beyond the scope of hard real-time systems. So high resolution timers are generally useful. Threaded interrupts are really useful, particularly if you're working with things like I2C and other slow buses. But the major invasive hooks that underpin preempt RT, and that we'll discuss coming up, have still been maintained separately until 5.15. So 5.15 is the kernel which was released containing a large quantity of the preempt RT kernel code. It's one of the reasons why we've chosen to schedule this course at this time, because it's when people are starting to think about this now. Now they know it's going to be upstream. Now it's really, really clear that it's on its way and it's very, very soon. People have to start planning for this. So it's a very significant feature merge, but it's not yet activated because it's predicated on a config option called config arch supports RT. And presently, none of the architectures in the kernel have set that config option. If you're not familiar with kconfig, there's the user visible kconfigs that are also not user visible kconfigs, by which the arch presents to the kconfig system the features that the arch supports. So this is saying that there is no architecture that supports real-time at present. And so the preempt RT kernel patch set does still exist. And one of the things it does is it goes through x86 and ARM64 and sets this, as well as containing some bug fixes and other bits and pieces to make it all function. Okay, so history lesson done. We'll now look at what these different models are. Interestingly, I believe these models are actually also mapped to the timeline. So this stage one is clearly, early kernel 1.0 and onwards, and then we get the voluntary, and then we get the preempt. So it's actually in time order as well. So the initial model, preemption only for user space. That's called config preempt non in kconfig language, and it is that very, very simple approach. Once you're in a system call, it's your CPU till the system call ends. It can result in extremely large scheduling latencies if you're running complicated system calls. But it does give you good throughput. CFS will still observe the time that's been spent, and therefore it will compensate other tasks for their inconvenience. So fairness over the long-term average is still preserved. It's not that you get an unfair slice from owning the CPU. It's just you get the slice in a bigger chunk than you would otherwise have got. So it's, like I say, it's commonly used on server systems. And we're illustrating this as a sort of example task which runs in user space, makes some big system calls, and it is making some complex system calls. This kind of task is marginally unusual. At least to do this without sleeping is a slightly unusual pattern, but it allows us to diagram it quite nicely. So we've got these small bursts of user space and these long periods in the kernel where we cannot be preempted. Voluntary preemption is based on a very interesting observation about the system. So in order to try and get spin locks correct, fine-grained spin locking is quite a difficult thing to get correct because it's very easy to accidentally enter into a mutex while you own a spin lock, and if you do that, your system is at risk of deadlock because you're owning a spin lock but allowing other tasks to run. So there's a debug annotation added to the kernel called might sleep, and it basically says that on this code path it is possible for the thread to deschedule for some reason. And it's basically a debugging tool that allowed you to prohibit possession of spin locks at that point. So if you call might sleep, there was a debug tool, config debug atomic sleep, sorry, that would cause kernel splats to come up on your screen to tell you that your driver is incorrect and it is trying to sleep while it's owning a spin lock. The key insight that made voluntary preemption possible was that if it's illegal to hold a spin lock while you might sleep, then by definition, it's safe to preempt at that point because you don't own anything that is, you're not executing a critical section. By definition, if you can sleep, you're not inside the critical sections from an SMP point of view. And if you're not inside the critical sections from an SMP point of view, which is what stops the cores competing with each other, it's safe to preempt. It's safe to allow this core to change to other tasks. So yeah, this was a remarkable sneaky trick because might sleeps are scattered quite frequently through the kernel. So this gives us lots of potential points as we hit and take mutexes. Even if we don't sleep on the mutex, we don't give up the CPU. But now we can, because we're calling might sleep, and might sleep will jump into this conditional reschedule, and that gives us lots and lots of voluntary scheduling occasions, scheduling decision points. Like I said, this is a common setting for desktop and laptops, and we can diagram it kind of like this. The kernel still stays in these red sections for relatively long periods, but every so often, every time we call might sleep, we have this opportunity to preempt, and that is going to significantly reduce latency on any kernel copath that hits might sleep. There isn't, however, a plan to hit might sleep. It is simply using debug annotations. So it's certainly possible to have system calls that run for a long time anyway, because they never try and contend on a mutex. And because of that, we also have the preemptible kernel, which is known as config preempt. And this is the point at which we have implicit preemption in the kernel. So when it's not suppressed, we don't own spin locks, we can preempt at any time. So in this case, as soon as the task is made runnable, we actually set a little flag. This is the case for all of the modes. And then in this case, it will happen immediately. When that flag gets set, if there's no suppression, we will immediately make a scheduling decision and allow other people to run. If preempt is not 0, then at the point we set preempt to 0, if the flag is set, we will then make the scheduling decision then. So now we have the default to be preemptible. So we've got lots and lots of green in this diagram, even though we're in the kernel. But as soon as we take a spin lock, while we own the spin lock, we have this short window where we are not preemptible. So this has quite a profound effect on scheduling latency. It now becomes the case that making system calls no longer means that you get a big chunk of CPU and you get kind of lumpy scheduling where you've got big execution times of running these things. The final stage is the fully preemptible kernel, kernel preempt RT. And this is the point at which, rather than reuse other instruments, so if you think about it, preempt voluntary is reusing might sleep, and preemptible kernel is reusing the spin locks that we use to assure SMP safety. And for many people, config preempt came before we had access to cheap SMP computers. So we were benefiting from the SMP work that was done for Big Iron, as it was then, on our desktops for, before we hit the SMP era, we were still benefiting from preempt on our desktops, and we were still benefiting from the SMP work that had been done in the kernel. Anyway, just as an aside, fully preemptible kernel, config preempt RT. At this point, instead of reusing other infrastructure, there has been an active, conscious, deliberate effort to try and find ways to reduce to the absolute minimum periods where the kernel is not preemptible. And it does this ultimately by making it possible to use the Spinlock API and remain preemptible. And we'll look at how it does that in a moment. But the end result is that now, almost all the time, the system is preemptible, except for these tiny little bars when we pull into certain bits of code that by their very nature cannot be preemptible. So we still have, whatever we do, a certain number of hardware interrupt handlers. And when we're in those, the kernel isn't preemptible. But as soon as that handler exits, and we can make steps to make it exit really, really fast, we become schedulable and we become preemptible again. So we're now going to have a little tour of the features in preempt RT that make it possible to reduce those latencies without making massive changes to the kernel. Because the thing that makes preemptor RT both so hard and so clever is that it doesn't require very significant changes to the kernel. It makes big changes to its dynamic behavior without needing significant code changes. In general drivers, I mean, things like IRQ drivers have lots of work. There's lots of code to realize it, but the bulk of the kernel is in drivers / and to make preempt RT work, most of the drivers, that vast resource that Linux has of drivers, can be reused, and that is ultimately the goal for preempt RT. So the key thing that's happening is on a real-time kernel, all interrupt handling is going to be switched over to kernel threads, real-time kernel threads. This is a feature called thread IRQs. It's actually been in the kernel since 2011 because it's useful in other circumstances. And the basic idea is that you split the interrupt handler into a quick check handler and the bulk of the handler. The quick check handler, its only job is to verify that the interrupt is actually pending. And if the interrupt is pending, make some action to stop the flag being raised to the CPU. So we find a way to mask the interrupt somewhere, and then we exit. That's the quick check handler. And then we call a second half handler, which actually does the interrupt handling. It studies things, it makes the change, it changes the hardware. This gives us some nice properties. Once you've got threaded interrupt handlers, you can use the scheduler to prioritize them. So you can set shed FIFO particular tasks to particular levels. Interrupts will remain active throughout that, but they'll only be running their quick check handlers. But as we go into the scheduler, we've now got prioritized interrupt handling. More than that, we can mix together interrupts and other activities. So a classic example from audio workstations is you set your audio interrupts to be the highest priority in the system. You then put some of the DSP that is attached to the audio processing at the next level in the system. And after that, you have the rest of the interrupts in the system. That's a very unique thing for kind of professional audio workstations, but you can have tasks that sit at higher priorities than interrupts using this mechanism. Threaded interrupts allow drivers to perform sleeping waits in their interrupt handlers. This is one of the reasons that threaded IRQs are used for things like I2C, because when you're writing a driver for an I2C peripheral, simply reading and writing to its register sets is expensive, and you want to be able to sleep while you're waiting for the results. And finally, it can reduce the complexity of locking. When you think about, do I want spinlock or spinlock IRQ save or spinlock _ IRQ? Once you have got rid of spinlocks and replaced them with sleeping locks, you don't need to think about whether you've got to lock interrupts or not, because you don't. Once you switch to sleeping locks, you don't need to lock interrupts. There are some interrupts in the system that you cannot make threaded. So there are some things you explicitly say, I don't want threaded. So timer interrupts, interprocessor interrupts are both examples of things that you explicitly say, never thread this interrupt. Per CPU things, which are on ARM, is primarily for the performance monitoring unit and some of the one-shot stuff. So just to visualize it, a normal interrupt handling on a system that does not have threaded IRQs looks like this. So we've used the request IRQ API, we've put in our handler, we have our high priority task, we run the handler, and we go back to our high priority task. That's what you all imagine interrupts to be, I hope. Threaded IRQ handling. In this case, we have a high priority task that is higher priority than the interrupt thread. This is actually relatively uncommon, but it's showing the feature can be used. So in our threaded interrupt, we have split from our quick check handler and our thread function. So the handler is running as a normal interrupt. Then we go back to completing our high priority task until it schedules. And then we run the thread function. So like I say, quite commonly, the handler will trigger the thread function and it will preempt everything else in the system anyway. But in some cases it won't. So we have this potential wait for the thread function to run, but in exchange for that, this is a much better citizen, and it behaves nicely with other aspects. I'll draw your attention to this 50. If you wondered last week why my control loops have been set to 90 and my command and control was set to 40, it was to put it either side of the interrupts. On a system that's running control loops, it can be argued, not always, but it can be argued that those control loops are more important than the majority of interrupts. Because we're going to go and read a couple of registers to read our sensors, we're going to set the results that the controller gives us, and then we're going to go back to sleep. And if what we want to do is control that process, and controlling that process is the most important thing for us to do, we don't need to take interrupts while waiting for it. So that's the reason I put high priority for those and then drop down to a very small number like 40, is to split either side of the default interrupts. So preempt RT, what happens when you go to preempt RT? So preempt RT enables this thing called forced interrupt threading, which is mandatory for preempt RT. I think you can actually turn it on regularly, but it's mandatory for preempt RT. And at that point, when you force threading, what you're doing is you're making the interrupt handler that you provide to request RQ, or the quick check handler that you applied to a threaded RQ, run as a normal task. So what's happening is when an interrupt fires, we end up running in a piece of code that's supplied by the architecture, whose only job is to go to the interrupt controller and shut down, mask the interrupt. So that causes the interrupt flag to lower to the CPU, and we can exit again. So it masks the interrupt and it schedules the first level handler. The first level handler will then execute, and it might then jump through the threaded function as needed if you've got a thread function as well. But fundamentally, the thing that is taking the interrupt now, when you've got preempt RT, is not supplied by the caller. It is supplied by the architecture, and its only job is to reach into the interrupt controller and shut down the interrupt, and then schedule the real interrupt handler. That can have a profound effect on your interrupt latency, so that's why it's being done. There is a problem with this, which is that if we take a spin lock, we wouldn't then be able to preempt into our interrupt handlers. So we'd end up with long periods where we couldn't take the interrupts because of so we'd basically swapped interrupt latency due to interrupt locking to interrupt latency due to preemption disable. So the next thing that we do is we convert spin locks to mutexes. So spin locks are traditionally these spinning loops that are used to avoid multiple entry into critical section across SMP systems, and they're a performance trick. On a preempt RT system, that is replaced with a regular sleeping mutex that the scheduler knows and loves. And that will mean that you can take this lock here. In the handler, you can take the lock, and instead of deadlocking, I don't know if I've drawn it on the next slide, we have, haven't we? Okay. Oh, we've drawn it differently. Oh, sorry, I beg your pardon. We'll keep on this one. So we can take the lock, we take the handler, we take the lock here. At that point, the handler will block. The lock can then continue. So the original task can continue, and then the handler will run. So I think this is actually correctly diagrammed here. So getting rid of spin locks means that we've now got our hardware interrupt here. It's then triggered the first level handler, which may take a lock, which is a sleeping mutex now. So the thing that actually originally owns the lock runs until it releases it, then the handler comes back and completes the task. Now, when I say converted to mutex, we're not changing the API, because that would have a massive, massive impact on drivers. What we're doing is we're taking the spin lock API, so you still call spill_lock, but the implementation under the covers is actually taking a sleeping mutex. And it also means that spin lock and spin lock IRQ save do identical things, because there's no need to mask interrupts at this stage. So it does mean that the code becomes, you have to remember the effect of preempt RT, because you read the code and it's, oh, that's a spin lock with an IRQ mask, and it's not. Now it is a sleeping mutex. But because of the design of the rest of the system, it doesn't actually have a significant impact on many drivers. It will on some, but on most drivers, that doesn't actually have an impact on their correctness. Next step, RT mutex. So The default mutex that's used in the kernel does not include any kind of priority inheritance protocol. So on a standard kernel, if you are competing for mutexes within the kernel, you can have priority inversion, and you will have essentially you won't necessarily run the highest priority tasks in the system. And that needs to be addressed. So that's addressed by replacing all mutexes with RT mutexes. RT mutexes is yet another feature that grew up in the RT kernel, but was merged into the mainline kernel a long time ago. And the reason it finds a use in the mainline kernel is that it's used as part of the implementation of futexes, fast user space mutex, futex. And the futex feature is used by the C libraries to implement pthread mutexes. So in other words, when you use pthread prior inherit that we met last week, that is boiling down under contention to actions on RT mutexes, and that's where it gets its priority inversion avoidance from. So with a preempt RT system, all in-kernel mutexes and all in-kernel spin locks are switched over to use this real-time mutex. So now we have got hardly any time where we have to disable preemption. We've got priority inheritance avoidance, and we've got controllable interrupts that are prioritized. I think I won't speak to this slide. This is the same diagrams you saw last week as an explanation of what priority inversion was. It's mostly useful for when I deliver this talk without the preceding module. If you want to enable preempt RT in your kernel, you pick the stable preempt kernel that most closely matches your biz. You go to this website, you try and hunt down a preempt version that matches the vendor kernel that you've got to work with. Ideally, it's the latest upstream versions, but if you don't track that on your boards, you pick the BSP equivalent. Once you have applied that patch to your source tree, you can enable the config option, config preempt RT, and you now have a preempt RT enabled kernel, except for the possible driver bugs that may result. So there are some very big changes to the dynamic behavior of the drivers. The manner in which interrupts interact with each other changes their timings. Some of the scheduling orders change. And then, of course, you may also, so that means as you forcefully threaded interrupts, there are changes. And for low-level system drivers, they may not be using the correct spin lock API. Now, I'm going to explain what that means. So a little while ago, I snuck past you this quote that some interrupts, no thread per CPU one shot, typically those needed to manage the lowest level kernel features cannot be threaded. This is basically a message that if you're a regular driver developer doing quotes normal driver development, it doesn't affect you because you don't use this type of interrupt. But if you do use this type of interrupt, or you're writing an IRQ chip driver, you need to pay attention to this. So those interrupts are not converted to threaded interrupts. That means they're still normal interrupts. And whatever you do, it is still illegal for normal interrupts, those that are not managed by the scheduler, to use sleeping locks, because a process that runs outside the supervision of the scheduler, like an interrupt, cannot use scheduler-based locks. And that means that it is not allowed for any code based on these type of interrupts or an IRQ chip driver to use the spin lock functions anymore. And in actual fact, that's never been allowed, or at least for the last, it has been allowed. For the last 12 years, that hasn't actually been allowed. The kernel provides this thing called the raw spin lock API. The raw spin lock API basically provides the original spin lock API that has not been converted. This is still real spin locks implemented in the same SMP spinny ways that we've seen for decades. It's an annotation. It was introduced in 2010, but it has not been strongly enforced correct use of this API. So anything that uses this type of interrupt should have originally been written to use the raw spin lock API. If you are writing an IRQ chip driver, it should have been written to use the raw spin lock API. But many maintainers were a bit fuzzy about the difference between the two spin locks, don't select the correct ones all the time. And it hasn't been enforced by any kind of debugging tools either. So it is a very, very likely latent bug. And all I can really say about it is you have the tools in your hand to find sleeping while atomic. You have config debug atomic sleep. So after you have enabled config preempt RT, you should unquestionably run a good chunk of testing with config debug atomic sleep set so that you can find any incorrect use of the Spinlock API. Like I say, if you've got an IRQ chip driver, that's the first place to look, but it could crop up in other places that are using special interrupt features. I think at that stage, I'm actually going to take a very short break, partly so that you can just have a minute or two off from the deluge, and partly because I have to pop out of the room for a very short minute. Oh, and because my front light's falling off my monitor as well. So I am going to start talking again at 20 past the hour, unless you're in India where it's 10 to the hour. But at 20 past the hour, I'm going to resume. And I'm going to fix my light while I'm off air. So I hope to see you all very shortly. So just to say, I'm going to kick off again in 2 minutes. I am very happy if anybody has any questions or anything they would like to ask about anything we've covered so far. Like I said, I'm going to wait till 20 past the hour in case anybody else has left the room as well. But if there are questions, I'll be very, very happy to talk about those to kind of consume the next minute and a half. But if there's nothing coming up, that's fine. I can cope with that. So it'll actually be 1 more minute for those who are awaiting the next part with great interest. So normally I do a 5-minute break in the middle of these sessions. I think last week I skipped it because it was booked for 2 hours and it was a bit of a jam to get everything in. This one's running 2.5 hours. So there is just a little bit of time to be fractionally more relaxed. Okay, so we're at 20 past the hour, and I just want to talk briefly about, so we say the philosophy that many Linux kernel maintainers adhere to. Not all, but many. And that's with respect to throughput and responsiveness, because throughput and responsiveness are sometimes in competition with one another. I mean, we see that with the decreasing worst case execution time and decreasing performance that we talked about before. And that comes for a number of reasons. There's first the intrinsic costs of switching. The most of the cost of a context switch, particularly if it's for a long period of time, comes from refilling the cache that covers the stack that we're executing. Because as we run on, caches decay after we've changed tasks. There are also costs associated with managing state. So, I mean, I hope it's obvious, but mutexes have a much greater runtime complexity than spin locks. Spin locks were introduced as an SMP optimization to give us very fast entry and exit into critical sections, and to give us a fairly cheap thing to do if the other side is going to release the spin lock very quickly. Mutexes with priority inheritance are even more complex because we have to track the competition for the mutex and work out who has the highest priority and who to apply the boost to, and we have to unapply that all at the end. There can be additional state tracking overhead. So in exchange for going to stage 3, where we had pervasive preemption, we have to maintain a count of the number of times we've taken a spin lock, which is done by mapping to an atomic variable that we can add and remove. Sorry, a per-CPU variable that we can add and remove from. Not per-CPU, a per-thread variable. So let's get this absolutely scrupulously correct. Inside the thread structure, there is a preemption count that we have to maintain every time we take and release a spin lock. That adds to the state tracking. It's one of the reasons that preempt voluntary is so neat, is because it doesn't have a particularly significant impact on responsiveness, because it doesn't add any additional state tracking, because it's based on these annotations in the code. There is the cost of checking the flags when we're in might sleep, but we don't have to do any extra state tracking anywhere else. And likewise, obviously, as you go to threaded RQs, you have to schedule the tasks. Scheduling a task has a cost. So these will always create costs that reduce the full performance of the system. Now, throughput and responsiveness are not always in eternal conflict with each other. Config dynamic is one way you can let out the steam by giving you config options at runtime. In addition, as we've seen, many of the real-time technologies that have been merged into the kernel make the kernel better. So when we have competition, we can quite often turn to configurability, or we can try and pick solutions that are wins in all cases. But if there is an unavoidable conflict, throughput is very likely to win, because transactions per second do matter. Transactions per watt do matter. And I bring that up before I talk about soft IQs and tasklets, because soft IQs and tasklets, when you describe how they actually work, are quite peculiar. You think, why is it so peculiar? And ultimately, soft IQs are one of the best examples I can point at of optimizing for throughput. That's why they exist. They were there to make the network stack work better, and a couple of other components as well. But yes, they were there to optimize throughput. They are not natural constructs with which to build real-time systems, which is a shame, because you're running an operating system that has them, despite the fact that they're not natural things to try and build real-time systems from. So let's explain what they do. So soft IQs are ultimately or primarily used as means to defer work from real interrupt handlers. What that means is you can be in a hard IQ, a normal IRQ handler, and you can raise a flag to say, when you finish doing all your interrupt handling, then please leave hardware interrupts unmasked, but do something else before you return to normal scheduling. So they steal time from the scheduler in the same way that hardware interrupts do, but they do run with interrupts themselves unmasked. So if you've got interrupts that say read from the FIFO on your serial port, you're still allowed to get those characters and put them in a buffer, but you can't do kind of real scheduling. You can't do real work while you're doing these soft IQs. On a non-preempt RT kernel, so on a normal kernel, they also have some quite unusual semantics. So they can be raised from either normal or IQ context. If you call them from normal context, they will start running immediately and take over the CPU from you. If you run them from IQs, like I said, they'll be run as you run out of hardware interrupts to handle. They're run with interrupts enabled. And I say they're run when you leave IQ handler, but that's not quite true. They normally run when you leave an interrupt handler. But sometimes they run from a dispatch thread that is scheduled with sched other priority. And basically what happens is if you're spending too much time executing your soft IQs, then soft IQs are disabled except for the K-thread soft IQD. So in other words, they run just after interrupts run, except when they don't, when they go to a relatively low priority kernel thread instead. And then finally, unless they are running in this kernel thread, K-soft-IQD, the scheduler is unaware of their existence. They are also, like our interrupts, outside the scope of the scheduler. That means the handlers cannot sleep, and it means they steal virtual runtime from CFS processes, and they steal RT runtime from real-time and deadline processes. So we looked at both the execution time, what's it called? Period. I had this on the tip of my tongue this morning. Budget. So on a deadline task, you have the budget, and on a real-time task, you have those throttles that say if you use more than 95% of the CPU, stop running. Soft IQs steal runtime from those activities. So it's a particular problem for your deadline threads that when you're creating a budget on a non-preempt RT system, you don't just have to have a budget for your own execution time. You have to have a budget for your own execution time plus interrupts and soft IQs that might happen while you're running. And tasklets are simply a mechanism constructed on top of soft IQs that make it look like it might be a good idea to call them from drivers. I say make it look like it might be because work queues or threaded IQs are generally a superior alternative to tasklets. So you have work queues that can create K-threads and dispatch work. You have threaded IQs that can produce and run at sched FIFO. So in a lot of cases, threaded IQs are going to offer us a superior alternative to tasklets. There are quite often performance reasons why you choose to use tasklets. Ultimately, when you're performance tuning a non-preempt RT system and trying to boost the transactions per second, tasklets may occasionally look like a good idea, and they might be a good idea because transactions per second matter. But from a real-time perspective, they're difficult to analyze. They don't interact with a scheduler, which makes it really difficult to observe the damage that they're doing to the system. They have this crazy concept that they're the most important thing in the system, except when they're not, when they become one of the least important things. They are not analyzable from a real-time point of view. So if you're trying to say, do I meet my specification? The only thing you can really do is measure soft IQs, how long they spend executing, and try and put them outside the scope of the design. With preempt RT, things get rather better. There have actually been two versions of how soft IQs work with preempt RT. And a lot of the literature associated with preempt RT dates back to slightly before 2013. So the bulk of the design work associated with preempt RT happened back in kind of 2010, 2011 kind of timescale. And the design has been pretty stable since that point. The fundamental concepts of how it works have been pretty stable, and it's all been about bug fixing and shifting code into the regular kernel and trying to be confident it's not going to produce very significant regressions and maintenance workload for people. The thing that has changed over the years was soft IQs. So the early versions of PreemptRT, the reason I mention this is so the literature is worth reading if you want to dig into this deeper. But if you find yourself looking at old versions of the literature, be aware that it's describing an old version of soft IQs. So threaded soft IQs were the old approach, and they acted just like we described regular IQs as working. So for every soft IQ, we created a new thread, and that thread would run the workload. And the reason that was eventually moved away from is because it was proving very, very difficult to tune those workloads. Because to get performance up, you had to boost the priority of the soft IQ threads. And then because it didn't have the pressure release valve of moving them back down to the other schedulers during overload, you would end up with a thread dominating the system that you didn't want it to. Incidentally, this strange property of switching down to sched other is substantially to do with the fact that the network stack makes heavy use of soft IQs. And in a normal case, when you're not under a denial of service attack, what you want to happen is you want to process your network packets pretty much as early as you can and get them thrown down into the application queues so that applications that are competing for CPU resource have the network packets when they want them. However, when your system is under a DOS attack, or it's simply in some other kind of packet storm, you do want it to do something other than dequeue packets in the network stack, some from the network hardware. And so the reason for this overload mechanism is it basically means that if you are being attacked by soft IQ workloads, classically network packets, they become less important so that you can actually process the packets you've already got. And that was what made this so difficult to tune, is because if you boosted the priority of the networking stuff, it would dominate the CPU under difficult conditions. So the more modern version, it was also suffering from poor performance because it was involving extra context switches for something that was designed to be used during, it was a performance trick. Soft IQs were introduced to try and solve performance problems. So if you haven't got a fast path, then you've basically found the places where we know there are performance hazards and made them slow. And that's actually probably the bigger reason why things were changed. So the modern version can be best described as no more victims. And what that means is that the system can remember which thread raises a soft IQ and then make that thread responsible for handling it. So in other words, when you raise a soft IQ from something that is schedulable, the soft IQ itself will execute within the context of that thread, which means somebody who raises a soft IQ has to pay the cost of servicing it. Which does mean that you don't get unrelated processes being victimized by load induced by soft IQs. Soft IQs can still be raised from places that are outside the scheduler, timer IQs, per CPU stuff, things like that. They will be deferred to something like ksoft IQD. So at this stage, all soft IQs are run from scheduled entities. In general, if you raise them from threads, that thread will pay the cost of servicing them. And we do have this ksoft IQD to pick up the last few bits and pieces. I'm just going to segue very briefly to networking. So as I've said, networking is probably the predominant user of soft IQs by volume. And the way it works is that the new API, which I think has been new for nearly 2 decades at this point, is part of the networking stack that arranges for the RX particularly, but the packet TX and RX to happen during soft IQ. And they're raised from timers. And that's designed so that you raise an interrupt, so you raise a timer. In a normal situation, you will have accrued packets in that interval. Network packets arriving into a server is normal operation. You don't need to be told that there are packets coming. That's normal. So the event, the TX interrupt, sorry, the RX interrupt on a network socket, network card is not actually very useful because we could just wake up and assume there are some packets for us to process. So that's what the network stack does with the new API. It's a callback that runs from soft IQ. It polls for all the packets got available, and it dispatches them to the various queues that it needs to sit on. that will remain as you switch over to preempt RT. And because it's time triggered, it's very likely to be executed by ksoft-rqd in most cases. So the rough, I can't go into great details of time sensitive networking and other things, but there's two kind of bottom sentences. The first one is saying that if networking is outside the scope of your real-time system, so you've built a real-time system, the industrial control example in our early ones, perhaps, then networking is not part of the real-time system. It is perhaps used for command and control, but it is assumed to be outside of the real-time scope. In that case, it is very likely that CFS will do a good enough job of handling any work that gets deferred to ksoft-rqd, for the simple reason that if you've got light network load and not too many real-time threads, then network RX will be at the front of the non-real-time work, because under light network load, we aren't actually doing that much work from ksoft-rqd, therefore it's asleep most of the time. Therefore, when it wakes up, it tends to be on the left side of the graph anyway, which is what we want. And as we overload with packets, ksoft-rqd will become CPU bound, at which point it will be fairly scheduled alongside other things, and we get to do work other than just filter network packets. So yeah, the CFS has arrived in some of the intervening time while preempts being worked on, and yes, the assumption can be that it will do a good enough job of network management. If, however, real-time networking is within the scope of your real-time work, then you have to think about what it means to have soft RQDs and what level you should run it at, and so on and so forth. And so the one thing I would strongly suggest is that you look at a thing called nappy threaded mode. Nappy threaded mode was introduced in, I think, 5.12. And it's an optional to replace soft RQs with K threads to dispatch the TX and RX activity. So it's still effectively deferred work, just as Nappy has always been based on with soft RQs. So it's still deferred work, but instead of deferring that work to soft RQ, we defer it to a K thread, which allows us to set the priority for particular network devices differently, and potentially different, I think, different queue. If you've got a multi-queued network card, I believe you can set the K thread for one queue to be different to the things for K thread for another queue. That can allow you to arrange to have fast paths on some network adapters and not others, which can be the trick to maintaining, to minimizing the cost and preventing packet storms from doing harm, because they should be routed in other ways. It really is dependent on your hardware and your use cases and a whole bunch of other things. But the advice I have is, if time-sensitive networking is something you have to think about, then you should very, very much look at this technique to try and make the network more controllable and more tunable. Okay, so that's the end of preempt RT. I'm now going to do a segue into something quite different. It's going to be timers and timekeeping, and that's mostly to introduce to you the difference between different types of timeout. Because just as we have a strong difference in Linux between non-real-time and real-time processes, it is also useful to think about timeouts in two dramatically different ways, and the Linux kernel is designed around thinking about timeouts in those two dramatically different ways. So first off, just a quick look behind the scenes at drivers. So there are two fundamental types of drivers that get involved in timekeeping. The first is called a clock source, and it's simply a hardware abstraction of what's essentially a free running counter. Certainly if it's a 64-bit value, it's a free running counter. If it's 32, it has to interrupt before it wraps, but that's a minor detail. And the purpose of that clock source is to provide a timeline for the system to tell you where you are. There can be many clock source drivers within your system. You know, if you have a source of time, you can write a driver for it. That driver can be described in a device tree. The device driver can be loaded. And the kernel will then have to decide which clock source it's going to use. And it does that by using a rating. So any clock source that's provided to it gets a rating associated with it. The first strata is noted as only available for boot up and testing purposes. which means the clock is very nearly useless. One example is a spinning loop. Even if you've calibrated the spinning loop against a real-time clock, which is not useful as a clock source because the resolution's not good enough, even if you've calibrated your delay loops, time will only pass while you're spinning. So you can implement a clock source based on spinning, but it has this rather odd property that it doesn't actually count very often. So such a clock would only be useful for boot up and testing purposes, because you just update it from the idle loop. Once you go to higher things, you hit more useful clock sources. So functional for real use, not desirable, something that's correct, something that's correct and fast, and something that's ideal. So the ideal clock source is very cheap to read. It's high resolution. It's got lots of bits within it, so it doesn't wrap very easily. And once you have one of those, why would you use the second best clock source? That's the key thing for these ratings, is that once you can rate the clock sources, the driver tells you how good its clock is. The kernel will use the best clock source available to it, and the second best clock source is unused. There is one tiny exception, is that the ideal clock source can stop ticking when you go into power collapse modes, and so there can be a secondary clock source that gets flipped to count time while the ideal clock sources are stopped. But other than that, which is, like I say, a fairly small implementation detail, the primary clock source, the ideal clock source, will be used if there is one. And on 64-bit ARM systems, there is a clock source that is essentially close to ideal. It's called the ARM architecture timer. It's very cheap to read because it's accessed through the coprocessor interfaces. It has support for virtualization, so even within a hypervised operator, even when a virtual machine within a hypervisor, it's still cheap and easy to use. So yes, this driver is always present on ARM 64-bit systems, and it's almost always the best clock source available to us. ARM v7 systems also have ARM architected timers, but they're not attached via the coprocessor interface as far as I remember, so they're not quite as optimally quick. Quick aside about the scheduler clock. So in a moment, I'm going to just introduce you to a thing called the scheduler tick. And before I do that, I wanted to express that that's not the same as the scheduler clock. The scheduler clock is a clock source. It's a time source. It's a special time source because for the type of activity that it gets used for, it is prepared to sacrifice a certain amount of accuracy for speed. And that's because scheduler clocks are called from critical paths within the system. And if we have expensive reaches out to memory map registers, the scheduler will actually make slower scheduling decisions. And if you slow down the scheduling decisions too much, the scheduler latency climbs up and we have problems. So you don't have to supply a scheduler clock implementation. There is a default that's based on the Jiffies, the Jiffy counts. But if you have access to a fast to read clock with better accuracy, you can register that. Again, the ARM architecture timer happens to be a fast, easy to read clock. So on a ARM64 system, the scheduler clock will actually be using the same clock source as the regular timekeeping systems because it's comfortable and fast. It's actually all part of the same C file. So the clock source, when you register your arch counter, will actually register with multiple subsystems. So it will register as a clock source, it will register as a scheduler clock provider, and it will also register as a clock event, which is what we're about to look at next. So clock events are, I don't know if it's the reverse of clock sources, but they do the opposite of a clock source in that they, instead of free running and counting time, they take a time that you want to reach and calculate the values that you poke into hardware timers to arrange for the event to happen at a given point in the future. But like I say, it's quite common for clock events and clock sources to use the same hardware, but they don't have to. You can use a countdown timer as your clock event and a free running timer as your clock source. And I believe that what will happen is the clock source's overflow point will be calculated in advance, and then clock events can be used to roll it over so that you don't lose track of time. So they interplay. But ultimately, it's a device that fires an interrupt after a certain amount of elapsed time. On SMP systems, it is normal and also optimal for there to be a different clock event source per core. So again, the ARM architecture timer is instantiated per core, not per cluster, so that we can program the clock events on a per CPU core basis. And that's because the queues that we have, the wake-ups that we might have associated with a particular core will be different to the other cores in the system, because threads running on it will be waking up at different times. So we don't have to merge them all into one queue. The clock event device is also used to create the tick, or the scheduler tick. And that's a periodic event that does a whole bunch of housekeeping. So if you're familiar with Jiffies, which is a low resolution clock that allows you to keep an approximate track of time within the kernel, that's what the clock event tick does. It increments Jiffies by 1 every time we tick. We call it the scheduler tick because ultimately it's also involved in things like process counting and time slice expiry. So CFS, we've said we're going to give you a fair amount of VRun time. During the scheduler tick is when we look at the VRun time that the task has so far accumulated and figure out if we want to yank it off the CPU and replace it with a different one. So we don't calculate how much the budget of a task, we do calculate the budget ahead of time, but the place it is audited from to verify is the scheduler tick. It also does things like load accounting, it manages PELT and a couple of other bits and pieces. It will also do things like read, copy, update callbacks. It will dispatch some of the work queues. If you've asked, IRQ work is a particular type of work queue that allows NMIs to defer work to IRQs. So when an NMI happens, it eventually has to send a message to the kernel to say usually that PMU events have happened, and it does that by dispatching IRQ work. The scheduler tick defaults to a fairly low frequency. The default is 100 Hertz, which means 10 milliseconds at a time, and that's the default. And that means that your most granular wake up that you can do on a system that only implements scheduler tick to manage time is to wake up on 10 millisecond boundaries. You can change config hertz quite often to 250 or 1000. And the reason we don't do that so much these days is because we have also now in the kernel got high resolution timers, which allow us to use the same clock event source to give us high precision wake ups. So there's some more fragments of code from exactly the same C code that I've shown you before. We can see timers registering in different forms. So in timer setup, we've got some more clock events to register. We've got a rating again to say this is one of the best or better clocks in the system. You can see we request a per CPU IRQ, which is interesting for two reasons. The first, obviously, is that it's telling us we've got one timer per SMP core. The other thing is that per CPU IRQs are one of the things that cannot be converted into threaded interrupts. So we should be expecting this mechanism here. If it's having to use any kind of locking, it should not be using spin locks without prefixes. And that now gets us on to thinking about the nature of timeouts, because there are two ways that we can program wake-ups at some point in the future into the kernel. The first one is called the timer wheel, and the timer wheel is primarily used for timeouts. So this doesn't mean waking up at some point in the future to perform a task. It's usually a guard to check against something that does not occur. So for example, networking stack, you've got the SYN, SYNAC, ACK sequence. So if we receive a SYN, we send a SYNAC, and we also create an entry on the timer wheel to allow us to delete the session information if we never receive the ACK. So if the other side never sends us an ACK, we have to set a timeout for some point in the future so that, but that's not the normal case. Normally, when somebody sends us a SYN, they have every intention of opening a network connection, unless it's a denial of service attack, which means the normal case, the expected case, is for the event to happen and the thing to be removed from the timing wheel without ever timing out. An even more obvious thing of it being normal to remove this thing is timeouts on disk activity. So whenever you launch disk transaction on Linux, it will stick an entry in the timer wheel to say, if my IO event hasn't completed in the next 5 seconds, let me know and I'll reset the disk. And I have a machine on the floor next to me here, which I'm talking to you through. And as far as I know, it has never timed out reaching onto its hard disk or SSD. So every time I've spoken to that for the last year, it has put in a timer entry and then withdrawn the timer entry because it was not needed. So that's the timer wheel. And the key insight onto timeouts is, do you really need a particularly high resolution wake up for these things? No, you don't. You're simply there to guard and tidy up, roughly speaking, after an amount of time has elapsed. So the timer wheel is not optimized for precise wake ups. It's optimized so that the add and remove paths can be as cheap as possible. And the way it does that, and its fixed expiry is also as cheap as possible, because the scheduler tick is happening 100 times a second. We don't want it to waste time, so we also want the timer wheel to be efficient in checking that nothing is timed out. So the way the modern timer wheel works is actually as a cascading selection of timeouts, which have different granularities. And this is all based on that idea that precision is not that important for timeouts. Sure, if you're setting a timeout in 10 milliseconds time and you wake up in 2 seconds time, that's a bad thing. However, if you set a timeout for 30 minutes and you arrive 2 seconds later, that's almost irrelevant. So we have these multiple levels, and precision decreases as we get longer and longer waits. So the longer you sleep for, the further down this level you will go, and you'll be put into a particular queue with a particular granularity. And that means that every scheduler tick, we examine level 0, but we only examine level 1 every 8 ticks, and we only examine level 2 every 64 ticks, and so on. The API, yeah. So that's the essence of timer wheel. It's based off the scheduler tick, and it's deliberately imprecise in order to make queuing and dequeuing efficient and fast. High resolution timers are the opposite. These are things where we expect to need a precisely timed wake up. In the example of the control loops from our embryonic example, that means that when we call, if we do nano sleep, we run our PID controller and then we call another nano sleep. We want that to wake up relatively precisely. We don't want to get an excessively long sleep. Likewise, when we're selecting and saying there's a limit when we are using interval timers. So the various user space techniques that I spoke to you about last week, nano sleep, select, poll, and so on, are all going to use high resolution timers by default. And in kernel users that need a precisely timed wake up. So when it's not a timeout, if you're doing multimedia and you need to be doing some activity 25 times a second to go and read a frame off a camera, that's a reasonable use of high resolution timers. So they're fully available to the kernel as well as, to the kernel code as well as to user space code. High resolution timers they're viewed as having nanosecond resolution, but they don't necessarily have nanosecond granularity. So you can request wake ups down to nanosecond resolution, but different clocks will actually implement different granularities. So you don't necessarily get nanosecond precision. There are also ways to have constructive ambiguity to allow more power efficient clustering of interrupts. So you can actually say high resolution timer within this window. But ultimately, that's what high resolution timers are for. They're for precisely timed wake ups or precisely or well documented degrees of indecision. So there's a quick summary of the API. That's mostly just to give you a starting point if you want to do any code browsing. But again, as a driver author, you have to think carefully about what type of activity you're queuing for. If it's a timeout and it's relatively unimportant how precise everything is, you've got the timer wheel API to work with. If you are creating something that needs to have a very regular, well-timed event, HR timers are there for you to use as well. And the final aside, before we go into a couple of tools and techniques, is to think about power management. Because power management is a risk to real-time systems. It can be mitigated, but it is a risk. And that's because we'll be jumping and putting the examples up on the screen. So as we go to sleep, there will be a point at which we have irrevocably started down the path to going to sleep. So we start to mask interrupts, and if a interrupt for timer or any other thing arrives just after we've muted interrupts, then we're going to walk through the entire suspend path And then we're going to walk through the entire wake-up path as well. So this is important to understand. When you have a wake-up latency, which I talked about when we were looking at latencies, it kind of feels like wake-up latency runs on the bottom line, running from CPU on through to the IQs being enabled. But if you do not have some means to abort from these top sections, and these are now firmware features and outside the scope of the kernel, if there's not a mechanism to abort the attempt to go into low power states, then the longest latency actually occurs when a timer comes just as we've irrevocably decided to go to sleep. We then work through all these steps and through all the wake-ups as well. And to be clear, some of these steps are quite expensive. Particularly if we're going to turn off caches, we have to flush them first. So if we're going into a power state where the caches are unpowered, we might have to flush L1 or L2 caches, depending on whether we're taking cores or clusters down and so on and so forth. There is also simple entry and exit time. It can take time to bring things back up and get them online and so on and so forth. The hardware latency associated with this is entirely platform dependent. So whether it's going to produce a problem is going to depend on your hardware and what you do with it. It may also depend on your firmware implementation, because you might be able to do things like, while you're flushing the cache, recognize that a signal's come in to wake us up and abort. Right. So this is mostly just kind of warnings, and there are multiple mechanisms you can avoid it. I mean, the simplest thing is you can avoid some of the low power machinery and not use it. So if you have a system where you've looked at your real-time specification, you've recognized that going into a very deep sleep state means that it's possible to meet the specification, then you can disable that sleep state. On ARM systems, an interesting starting point is to say, we'll turn off everything except WFI. And if you're industrial, that's a very easy thing to think about. WFI does clock gating, but doesn't really get involved in power on or off, although it is defined by the microarchitecture. So different cores can implement WFI in different ways. If you have systems that are modal, meaning sometimes they have real-time characteristics and sometimes they don't, I'm reluctant to wave a phone at this point, because while a phone is clearly a modal system, it's not usually a real-time system. Although there's no reason why it couldn't be in some areas. So if you have a system that is modal, that it goes into a mode where we want to have real-time constraints and we want to come out of it again, and I suppose perhaps an audio workstation that isn't recording could be an example of this. If we're not currently recording something on an audio workstation, we often don't care about the real-time behavior. As soon as we turn on the recording mechanisms, then it becomes expensive, because if we miss our real-time deadlines, then the band have to retake, and we retime using the studio and so on and so forth. It's one of the reasons Pro Audio was an interesting use case for Preempt RT, because it eventually became dollars. So if you have one of these modal systems, you can use latency constraints. So entry and exit times into low power states are usually described in an ARM system that we described in the device tree if it is a embedded system. And you can basically say, I do not want to go into these modes if it's going to cost me more than this amount of time, and then those low power states will be disabled. But you can, they can be raised and lowered dynamically as needed. And then finally, you also have to think about CPU freak switching costs and appropriate minimum frequency. So CPU freak, if you're running at low speed, you have to be able to either meet your constraints at that speed, or you have to be able to switch to a higher speed before you've missed your deadlines. So that's a matter of figuring out what the switching costs are and whether there's appropriate min freak. Or again, if you're on a relatively simple system, then some people just turn it off entirely and say, well, we don't want CPU frequency switching. We'll just run at the lowest speed, which we can sustain and call that our speed. So it's not that power saving techniques are invalid in real-time systems, but they add an extra hazard that you have to analyze and mitigate. So we want to say that quite kind of loudly, and particularly the costs of entering and exiting these states will contribute to latencies. Okay, so the final thing we're going to look at is a couple of tools and techniques and a pretty graph. So the very purpose of Preempt RT is not to make anything faster. we lay this on over and over, and everybody involved in real time says this all the time because it gets misinterpreted. It's not to make things as fast as possible, it's to make it as fast as specified. And so we've got a graph. This one comes from a Red Hat Enterprise system from a couple of years back, showing a visualization of what can happen to the performance of the system. It's surprisingly hard to hunt down performance figures for preempt RT, and that's ultimately because they'll be the same on they'll be different on every different piece of silicon. So every new machine will have different workloads, which we're calling different system calls, which means the worst cases will change. The actual physical performance of the system will change, whether you've got power management, not power management, all the different features. So generally speaking, this is a graph that you would make for yourself as part of your own work. So once you have got a baseline system, you would characterize your own system and then make decisions about whether or not preempt RT is necessary to build the type of system you're trying to build. It's quite possible to, if you've got systems where you can engineer in buffering to mitigate latency, what you can do is measure the typical performance and then set the buffers to a higher level than that. And then you don't need to go through the complexity of debugging preempt RT and things like that, or pay the performance costs. So it's not always the case you dive straight on preempt RT. And what we see on this particular graph is we've got the dense blue sections at the bottom, which are telling us that the best case execution time is in the non-real-time kernel, which is what you expect because non-real-time kernels do not have the same level of overhead. So the best case performance is better in the non-real-time kernel. But in exchange for that, the worst case performance is incredibly long. You'll notice down the left that this is a logarithmic scale. So this chunk here represents about 3-4 microseconds. This outlier up here represents 10,000 microseconds. So these outliers are genuinely a very, very significant long way out. And you get this kind of, if it's other than that, the patterns are very much the same. You have best cases that are very, very good, and you see the occasional green speck here at the bottom. You have a kind of default top and bottom range, and then you have a few outliers. And the key thing here is that my eyes, which aren't very good at color perception, but I don't see on this graph any outliers outside the 10 microsecond range. Whereas in the non-real-time case, I don't actually know whether that was a sched voluntary, sched non, or preempt kernel. Sorry, preempt non, preempt voluntary, or full preempt. I don't know which it was. But the outliers are a very long way out. And that's the sort of thing that I would expect you to see if you run these experiments on your own hardware, but you will not know the actual physical numbers. You won't know a number in microseconds unless you run this on your own hardware. So some tools to help you. Just to mention, this is cyclic test data. So this is basically looking for the worst case as measured by a tool called cyclic test, which is what I wanted to introduce you to next. So cyclic test is probably one of the most dominant tools for trying to benchmark real-time systems on Linux. And it's basically a methodology to attempt to measure the combination of all the latencies up to, well, it can even measure application latency, but it's essentially trying to measure all the latencies up to the end of scheduler latency. And it's using a technique that we introduced you to last week if you did the labs. So you've actually, if you've done the labs, you've implemented some variant of cyclic tests and we're using a similar methodology. You basically fire up a collection of sched FIFO test threads. You usually make them the highest priority task in the system. And they're basically woken up periodically at particular intervals. So in other words, we have set a high resolution timer to wake up at a particular time. And then we wait to see when we actually get scheduled. And that allows us to track the sum of all the wake up, interrupt, and scheduler latencies before we reach the high priority task. And if we're not the highest priority task in the system, we're also observing application latency as well, which can be useful if you want to try and characterize the real-time behavior of something that's not the highest priority task in your system. So that cyclic test, it can be used to capture this information. It's run classically like this. So you will notice we've got -mmoc all, which we see from last week, which is necessary to make sure we don't have memory effects disrupting the observations. We've created one test runner per core. We've set a FIFO priority. We've told it how often to run, and so on and so forth. And that gives us a min, average, and max that we can study and reason from. So that's cyclic test. Cyclic test is a really useful little benchmark for observing it. You will also realize that it is statistical. You're assuming that the wake-up times that you set on it are going to hit all the interesting cases if you run it for long enough. So it's a statistical approximation, a bit like profilers, of what you can actually see as your worst cases. But the fantastic thing about it is it measures some of the unmeasurables. It measures the firmware cost of waking up. And this is one of the reasons the RT guys really like this as a tool for PC-like platforms where you have a closed source BIOS that can be doing all sorts of strange things when you make calls into EFI or you manipulate the system in some way. So because cyclic test can also observe firmware related costs like the wake up time, it does give you a very good full system view. And like I say, it has in the past been used to say, well, this PC can't be used for real-time systems because its firmware is not adequate. And then you go and get a different PC. In the ARM world, I rather hope that when those things get, it's embedded centric nature means that there'll be more pressure to get the firmware fixed and so on. But, okay, so the next tool we're going to look at is RT-app. So RT-app is a method for producing workloads that can be used to stimulate the scheduler. It's basically a way to experiment with how the scheduler is going to act when certain types of scheduling characteristics of wake time and sleep time are presented to it. It can be useful if you've analyzed a real-time load and you then want to check that the scheduler is going to work with it correctly. If it meets the thing, you can use it to model workloads basically with synthetic tests to examine how the scheduler works. And RT-app is used primarily for that in the community. It is used by scheduler developers to look to say, for example, that tasks get placed on the right CPU, or that they spin up the CPU fast enough, or whatever else. So particularly if you're interacting between power management and real time, it can be used to create a simulated workload that will match your eventual specified workload and check that you're happy with the way it gets scheduled. It's not perfect, but it's an interesting modeling tool if you want to really study how the scheduler is behaving on particular workloads. The last of the kind of toolsy things I want to bring up is this thing called RT-IRQ. And I do not expect anybody here to actually run RT-IRQ. It's not what it's about. This is about showing you a concept and principle, which is that of tuning. So RT-IRQ is designed to tune preempt RT systems to work well for pro audio use cases. Or to put it another way, it tries to find the audio drivers and the IRQ threads associated with the audio drivers and boost their priority. And the idea behind that is then when the audio card delivers data, it's the highest priority thing in the system. Sitting below that is the DSP that gets triggered by the audio card having data to work on. And then you've got all your other interrupts. And that's a form of tuning. So you have the default tune, which is everything sits at shed FIFO, runs at 50. You've got the default tune of things like K-software IQD or your network K-threads. Again, they will come up with default values and their K-threads. And so after they have been established, you will have to reach in with a tuning tool like this. It's quite often a systemd service or something like that. That will go in and apply the tunings you want for your kernel and your application. So like I say, RT-IRQ is not going to be the shell script that you need to tune your system. It's not auto-tune. It is just there for a specific use case, and you will not have it in your kernel. But if you determine that you need to tune your system to improve its performance, you've benchmarked certain properties of, say, interrupt latencies, and discovered that interrupts are a bit too lumpy for a particular real-time thread, so you've got to manipulate things and move them around. This is what it's here for. So you'll have a service that is semantically equivalent, but it won't be based on that shell script. That's just an example of a tuning script that you run. And the final tool I wanted to put in front of you is ftrace. So ftrace is yet another of the features that was developed in the real-time preempt space and was merged into the kernel a long, long time ago. And its key claim to fame is that it doesn't just log things that have happened, but it also timestamps them and tells you when they happened. And that can be very, very valuable for studying real-time systems. So you've got this rich set of software events, both within the kernel and principal user spaces can also do it. And we can look at those events in different manners. So fundamentally, we've got function trace and function graph trace. So if you have a real-time system where you miss a deadline, the usual question you have when you miss a deadline is, what was the kernel doing instead of meeting my deadline? So this will help you look at the functions, how long they're taking, which threads are running. You can look at the scheduler events. So the scheduler software events will tell you about context switches, so you can find out which threads are on the CPU and why they didn't give way to each other. So where you have an error, it allows you to look and observe what's happened on the system. The other ones that are particularly relevant to RT are things like IRQ off, preempt off, and IRQ preempt off. These allow you to look at some different ways to look at the same thing that we were looking for with cyclic trace, which is how long we spend not able to service interrupts. We can look at, instead of as a statistical profiler, which relies on the event triggering while we are in the worst case, we can actually go looking for trouble. We can look for the longest period of interrupt lock in the system. We can look for the longest period while preempts are disabled. We can look for the combination of both, just the longest period where we're not able to preempt for whatever reason. That does not have the same property as cyclic test because things like firmware latencies cannot be observed using it. But it does allow us to measure very much the worst case interrupt latency by seeing how long interrupts are held off for. It allows us to look at the worst case scheduler latency by looking at how long preempt is off for, because IRQ off and preempt off usually dominate both of those latencies. By actually tracking the direct usage of them, we don't have to hit a probe point. We don't have to test. If ever interrupts are locked for too long, ftrace will record it. Regardless of whether you're running cyclic test, regardless of anything else, if you ever lock interrupts for too long, ftrace can record that for you. I'm not going into great detail about how to run ftrace at this point. Entry point is this directory, which is part of debugfs once you've done all the config options. There is a little readme in that directory to give you some reminders of how it works if you've used it before. Otherwise, you can look at wrapper tools such as trace command or perf, or even perfetto, that can be used to establish ftrace scenarios without having to go directly to this directory and poke at files. And finally, you have things like kernel shark or trace compass that can be used to analyze the data coming back from ftrace. So there's tools at your disposal to help you solve these problems. This big table is probably less relevant to an audience comprised largely of Linux people. It's more interesting for people who've got a history in real-time operating systems because we're looking at the difference between the two. For us, I think the main things I'd like to call out is the Linux kernel has that really strong contrast between real-time and normal tasks. So we can have these different scheduling classes. And for normal tasks, we have CFS to take the base load. That is what is not present on traditional real-time operating systems. They tend to be FIFO round robin only, or in the case of QNX, it's got this rather interesting sporadic scheduler mode as well. It's, as far as I remember, that sits. I read about sporadic, and it's fitting into the same kind of niche as deadline, but using some slightly interesting and different techniques. But yes, you really notice that with the real-time operating systems, you don't have the capacity to use nice values to manipulate fairness. So you have to put everything onto the real-time scheduler, and then you have to prioritize everything accordingly. The other one, of course, is to do with weight and size and priority inversion potential. Particularly mainline Linux has features missing. We don't have threaded interrupts. We don't necessarily have complete preemption for non-user space. and so on. So that gets us close to the end of the talk. I'm going to take a brief moment to talk about developer services, and then I'll talk about the lab sessions. So Linaro Developer Services, that's the group in Linaro that I work at. And for people who are members, your primary relationship with Linaro is with the collaborative engineering side of Linaro. So that's where all the different members cooperate together to work on problems that are in their mutual interest. Sometimes, however, you have problems that are in your private interest. Either you want to get features that have been worked on collaboratively to work on your specific hardware. You might want to look at various security techniques that you could use to set up a secure boot and other things that can be difficult for your customers to set up. You might want to be looking at new ways you can leverage different open source products. If that describes anything that you're doing, there are many people you can turn to for help, but one of them is Linaro Developer Services. We have access to the same pool of expertise that we use for the collaborative work of Linaro, but through services, we can provide it to individual companies to focus on specific issues related to their specific products and hardware. Moving on from that, obviously training, you may guess, is a significant thing for me. I contribute a lot to the training at Linaro. Like I say, we chose to run this to members right now because PreemptRT is just in the process of landing upstream. We think it's a timely opportunity. We have many, many other training courses. If you work for a club or core member of Linaro, then we can potentially come in and offer additional courses delivered exclusively to the member without any additional charging, unless you've already used them all, of course. We can provide additional services to club and core members beyond the free of charge stuff, but if you are a group member or a project member, our training services are absolutely available to you as well, although we do charge commercial rates for those. If you have any interest in that, we can provide you with a full catalogue of courses. We've got a catalogue of all the off-the-shelf courses we have available, and I'm always happy to talk about other options as well. Finally, Linaro Developer Technical Support is another part of the Linaro space that I end up managing, and we are here to help all members, club, core, project, and group, or group and project. So the role of LDTS is to stand behind the work of Linaro. So anything that Linaro is working on, we are here to stand behind and help you with it. So whether that's something that Linaro has enabled in Kernel or anything like that, and you want some guidance, you don't want to push out to services and have somebody else work on it. You want to work on it, but you want some advice. We're here to help with that kind of thing. And it's all online based, and it can be as simple as just shooting an email and it will be picked up by our ticketing system. And it will be picked up by somebody from my team, but we are helped on the back end by all the other engineers at Linaro. We can reach out to anybody at Linaro to help us find an answer to your problem. So we are here to help. If you do want to take advantage of LDTS, you can find us by email. If you have remembered, support@linaro.org. You can just shoot an email. Make sure you use your company email address so that you benefit from the additional services we give to members. If you send it from a private email address, we take longer to reply to you and we give you much shorter answers. If you go through a web browser, you can look at support.linaro.org. You can self-enroll there, again, with your company mail address and raise tickets that way. If you just remember we do support at Linaro, but you can't remember how to find us, we have put some pains to try and arrange for Linaro support to score quite highly in most search engines. It would certainly be expected to be on the front page and probably in the top 3 or top 5 answers. Linaro is not a terribly common word, so we don't get too much crosstalk from other places. So Linaro support should bring you to the right place fairly easily and effectively give you a website that reminds you of these aspects. That hits the end of the presentation with exception to the lab sessions. And the key thing I want to mention to you to the lab session today is we have provided a basic lab session to allow you to run a preempt kernel. So there's a preempt kernel in the shared folder. You can download it, you can boot it, you can run cyclic tests. More than that, you can run Hackbench as well. So if it will depend on your host hardware, but if your workstation environment is nice and stable and relatively quiet, you have a good shot of observing Hackbench reducing the performance when you run on a preempt RT system. It's not guaranteed, it does depend on your host system. And that brings us to the second problem, which is that running on a simulator doesn't help. It can let you observe the costs of running preempt RT. It does make it more or less impossible for you to observe any benefits. And the reason you can't observe the benefits is that the host kernel is not RT in most cases. You know, my system that I'm talking you through here is preempt voluntary. So it does exhibit occasional chunks of latency. In order to run and benchmark preempt RT, you have to be running it on real hardware. And ideally, you want to be running it on your hardware. So the second lab ultimately is that if you have your hardware from your member company that sits on your desk, the very best thing you can do to try and better understand preempt RT is to make it run. It's not super hard. In theory, you're applying a patch, changing a kconfig, and booting a kernel with the debug options set if you're worried. This is a suggestion of how to do it. So this is a cheat. This is not how you would do it in production. But I'm aware that many vendor kernels are slightly out of date, may not be tracking the latest version of the stable kernel and things like that. So the suggestion I have is you basically try and find the appropriate patch that matches the version so that you get the fewest merge conflicts while you're playing. Once you have combined everything and applied this patch, you should be able to put the config on and boot it. So this will give you the smallest possible number of merge problems. And then it's a matter of chasing down any issues between spinlock and raw spinlock and any other timing issues that have been changed by the big dynamic changes that happen in real time. If you're very comfortable doing merges, you might go straight to preempt RT in production. I mean, there is no excuse for not running the latest stable kernel with the latest preempt RT patches merged into it if you're going to give kernels to your customers to use in production. So when you go to production, that's a trick and it's a hack. It's designed to get you up as quickly as possible because this is just a lab exercise. If you are going into any kind of production, do not do it like that. Make sure you're running most stable, latest security fixes, latest version of RT. Okay, so that gets us to the end of our time together. I hope you found it interesting. If you have any further questions, comments, or anything you want to raise before I disappear, you're very welcome to put that in the chat. If 5 minutes after we close the session, you think, oh, I forgot to ask, you still have support at linaro.org to raise any questions you have that may have come up during the training. I'd be delighted to hear from people. You can also expect to get copies of the video and a evaluation form from Christine in the next day or so. So we'd appreciate your feedback as well. It's very helpful to us to have these things. We use it for two things. One is we fish through them looking for useful testimonials. So if you have the freeform text box and you put in very nice things about us, we might well grab that as part of our list of useful quotes. We also look at the stats to make sure that we have covered the bases correctly, and I do also read them looking for ways to improve the course. So there are lots of things we use it for, but there's the mix of looking for useful quotes, checking that we've got the basics right, and looking for freeform text that helps us to improve in the future. So with that, I've given you 10 seconds of additional spiel to let people type questions if they would like to. I can't see any at the moment. So that gets us to the end of our time together. Thank you very much indeed for spending time with me. And I hope to see some or all of you again in the future.